Hello, I'm Wade from the Huawei High Silicon department. Storage is a very important field in the server market. There are about one of three. Except traditional storage, SDS means software-defined storage is very important at present. Many companies have almost established SDS and or operate teams. Now, I will introduce the Ceph optimization on ARM servers. PMEM 920 had up to 64 cores based on ARM v8.2. In addition to the autonomy of the cores, PMEM CPU also has rich I/O interface, which is very suitable for storage applications, including PCIe 4, 100 GB network, 60 SAS interface. There are also accelerators for general data process such as compression, encryption, hash, etc. Why we choose Ceph? Ceph is one of the most widely used SDS software in the industry. It has great advantages in reliability, performance, and a variety of business support models. It can support different work models such as block storage, file storage, and object storage. At present, many customers have taken Ceph test as a standard storage test program. Why we choose Ceph flash or flash configuration? In HDD-based storage, the bottleneck mainly from HDD. Using the minimum CPU, it can support 36 to 72 or even more HDD disk models. The optimization of HDD configuration has nothing to do with the CPU architecture, whether it is an ARM server or x86 server. However, in the all-flash area, because MAE has very high IOPS capability, especially in 4K random write, MAE is 1,000 of times higher than HDD. The software design makes the CPU to performance bottleneck. It only plays 10% performance level. We optimize the performance based on Ceph Bluestone, Nautilus, and Pacific version. Combined with the aarch64, mainly introduce NUMA deployment and balance, OSD thread schedule, page cache, CIC division, instruction appliance, network zero copy. In addition, the latency of block storage, especially in DB usage, is very important for DB user. We will introduce the IDPT persistent cache function for the latency solution. The software bottleneck, the CPU has reached 19 utilization. The IOPS is only about 200,000. Those software optimization, we can improve about 40% without software architecture modification. The effect is still good. The first is the NUMA optimization. NUMA is a necessary CPU architecture at present. In default configuration, Ceph OSD software will be randomly distributed on any core. In the worst case, software, network, MAE are located in different NUMA nodes. All I/O and network data stream need to be across the NUMA node with CPU efficiency and power consumption. Ideally, all network and I/O data traffic end at the one NUMA node, and all the data processed will not be across NUMA. Here is our optimization. 1. Ensure all the hardware resources are distributed in every NUMA node. OSD software automatically affinity to the node according to the hardware distribution. Avoid manually binding software process. In general, the network interfaces are limited. The network card only provides 2 to 4 Ethernet ports. We propose to use virtualization and the policy route to solve this problem. The virtual network card can be regarded as an independent hardware resource. Only this new hardware resource can be affinited to different NUMA nodes at the OS level, so that interrupt, channel, and DMA resources can be allocated locally. Through NUMA equalization, the performance optimized can be improved by at least 10%. Generally, it's a first operation for optimize. The second question is the thread balance of the OSD. Complex software systems are implemented by multi-thread and multitask currency, but the CPU executions are different in different states. It will lead to invalid system switch and inter-core switch. In Ceph OSD, we found several schedule imbalance problems. The first is the scheduling problem of KV thread. KV thread is responsible for writing metadata. It does not have much business process, but its I/O write operation will take a latency, currently designed for single thread. According to the setting, KV threads take more than 15% of the latency. How to improve the process effects of KV thread? We bind the KV thread, IO thread, and the interrupt process to different CPU cores to reduce the switch. It can improve by about 10%. Here we introduce the optimization of 64 key page size. Compared with 4 key 64 page size reduce CPU TLB miss and improve performance about 10%. CentOS threadhead has a 64 key by default in aarch64 system. Other OS need to compile the kernel for support. However, using 64 page size is a complex problem. We have found and solved some problems in the related software, not only in Ceph, such as bcache, tcmalloc, and kernel read. Now we introduce the instruction optimize. CRC is widely used in Ceph message RoDB data verify. Ceph message CRC optimization is realized from Luminous version, but RoDB, that is an independent software, not support CRC instruction before 6.3 version, because every software of the CRC computation realized by themselves. The division instruction, because aarch64 not realized 128-bit, so the long double division should realized by software. In the Ceph static, use long double to compute the second to microsecond and nanosecond. So the software long double division became a hotspot. But in the real, long double is not used in nanosecond compute. Double is enough, and the double division could use aarch64 instruction well. The CRC and double in division instruction will provide 5% optimization. And finally, the bottom of the network. We choose the kernel TCP zero copy scheme. TCP zero copy requires kernel version 4.18. The mainstream OS has been upgraded to this kernel version. which has a good universality, such as OpenOLA, CentOS 8, and so on. In addition, we only have realized the send direction, but not the receiving direction. There are some difficulties in the receiving direction, such as when the system crashes while the process exists. We also use RDMA to optimize the network. It can provide more than 20%. But RDMA is hard to deploy and increase costs. The next step version of Crimson, RDMA SPD key may be a popular configuration for performance. Okay. The following it describes the latency optimized based on RBD persistent cache. RBD persistent cache is that the data is writing to the local persistent storage and the remote node of the backup directly, pass the Ceph message and process. In the backend, asynchronously brush back to the Ceph storage cluster. Currently, two media are supported, PMEM and SD, but the SD scheme is not unstable. We use PMEM RWL method. In the hardware, the Optane memory not support ARM servers, so we select the BBU PMemory for RBD persistent cache. In BBU configuration, it can provide 38 GB to 64 GB non-valid memory space. Current RBD cache use 1 GB can meet the requirement. Because the BBU realizes the cache level data protection, it does not need software flash cache data and can achieve the extremely low latency. While the power failed or other unusual accident, BIOS will flash all the CPU cache data and memory data to SSD by the protection of BBU. From the test, Ceph RBD client latency can be reduced to 50 microseconds, and the IOPS can reach to 20,000 while depth equals 1. This is a very good performance. At present, most customers' need is 100 microsecond latency. It will have a very good accelerator for the database. Of course, this latency not with replicate backup. The backup will increase by more than 30 microseconds. How to optimize is a network. So on the whole, Ceph can stably provide good IOPS and latency solution on all flash area. It also performs well on ARM servers. It needs our help before the ARM became the default selection of external developers. Okay, that's all. Thank you.